January 1943, the skies above Europe were a brutal, ceaseless battleground. For the Royal Air Force, the war was a fight, not just of men and machines, but of relentless engineering innovation and industrial endurance. At the center of this struggle was the Rolls-Royce Merlin engine, the mighty heart that powered Britain's finest fighters and bombers. From the nimble Spitfire to the versatile Mosquito and the heavy Lancaster bomber, the Merlin was the indispensable force that kept Britain's hopes aloft. But by the winter of 1943, a silent crisis was unfolding. It was a crisis that threatened to ground entire squadrons, to drain morale, and to imperil the RAF's capacity to wage war effectively. The problem was small, almost trivial in size, a single bolt costing just $3. Yet, this tiny piece of metal would come to symbolize the fragile balance between technological triumph and catastrophic failure. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. To understand the gravity of the crisis, it helps to grasp what the Merlin engine represented. Developed in the 1930s by Rolls-Royce engineers, the Merlin was a marvel of precision engineering, combining power, reliability, and adaptability. By 1940, it had evolved into the backbone of the RAF's fighter force. The Merlin's success was not accidental. Rolls-Royce had invested years of painstaking research, refining the V12 engine to squeeze every bit of horsepower from its supercharged design. Each engine was a symphony of hundreds of components: pistons, cylinders, camshafts, valves, spark plugs, and bolts, all working in perfect harmony. Any weakness in this orchestra could cause a fatal breakdown. The Merlin powered Spitfires that famously stood against the Luftwaffe during the Battle of Britain, turning the tide of war in the skies. It also propelled the twin-engine Mosquito, the wooden wonder that baffled German fighters with its speed and agility, and the massive Lancaster bombers, carrying devastating payloads deep into enemy territory, relied on multiple Merlins for endurance and power. By 1943, over 8,400 Merlin engines were in service, distributed among hundreds of aircraft flying around the clock. Rolls-Royce had ramped up production with staggering efficiency. Yet, even as output increased, a shadow loomed. Unexpected failures were causing engines to fail prematurely, forcing aircraft to be grounded for extended repairs or lost entirely in combat. Engineers and mechanics on the front lines began reporting a puzzling pattern. Merlin engines were breaking down due to the failure of certain fasteners, specifically a small bolt holding critical components in place. The bolt was designed to withstand extreme temperatures, intense vibrations, and massive stresses during flight. But when it failed, it triggered cascading mechanical damage inside the engine. The problem was more than an inconvenience. It was a threat to the RAF's operational capability. Entire squadrons were forced to reduce sorties as maintenance crews struggled to replace damaged engines and track down the cause of the bolt failures. Spare parts were in short supply, and aircraft availability began to dip at a dangerous time when the Allies were preparing for intensified bombing campaigns over Germany. In workshops across Britain, engineers scrambled to diagnose the cause. Was it a design flaw, a manufacturing defect, or perhaps the quality of materials was slipping under wartime pressures? The bolt itself was a simple part, about the size of a thumb, forged from high-grade steel and treated for strength, yet it had to hold together the Merlin's supercharger assembly, a component that compressed air into the engine's cylinders to maximize power. If the bolt fractured mid-flight, the supercharger could come loose, destroying the engine from within. Manufacturing Merlin engines in wartime was a colossal challenge. The demand was unprecedented, and Rolls-Royce factories worked tirelessly to produce thousands of engines monthly. Skilled machinists and assembly workers were stretched thin, with many new workers, women, apprentices, and those from less traditional backgrounds, recruited rapidly to meet quotas. The supply chain was also strained. High-quality steel was scarce, and sometimes substitutions were made without full testing. To speed production, some parts were outsourced to subcontractors who lacked Rolls-Royce's experience and rigorous quality controls. This fragmentation introduced variability into the components, especially smaller parts like bolts. The bolt failures, therefore, were suspected to be due to subtle inconsistencies in material hardness and heat treatment during production. In particular, variations in the tempering process, the delicate reheating and cooling of steel to achieve the correct strength and flexibility, could render bolts brittle or too soft. The Air Ministry immediately launched an urgent investigation as reports of failures increased. A team of Rolls-Royce engineers, metallurgists, and RAF maintenance officers pooled their expertise to analyze broken bolts retrieved from failed engines. Metallurgists examined the fractured bolts under microscopes, searching for telltale signs of manufacturing defects or fatigue cracks. They measured hardness and compared samples from different production batches. The findings were sobering. It became clear that the bolts from certain factories were consistently failing because the tempering process was uneven. In some cases, the steel was overheated, weakening its structure. In others, cooling was too rapid, causing internal stresses and microscopic cracks. The variation was linked to inconsistencies in the heat treatment furnaces and the skill level of operators, issues compounded by wartime urgency and workforce turnover. Among the engineers leading the effort was Thomas W. Harding, a veteran metallurgist at Rolls-Royce who had joined the company before the war and was revered for his attention to detail. Harding understood the problem. The bolt itself wasn't inherently flawed in design, but the production quality was the critical variable. Fixing it required tightening specifications, retraining furnace operators, and implementing rigorous testing for every batch of bolts before assembly. But time was the enemy. Every hour that faulty bolts remained in circulation meant more engine failures, lost aircraft, and lost lives. A crucial breakthrough came when Harding proposed a small but significant redesign. A new bolt, manufactured to tighter tolerances with an improved heat treatment protocol that would make it more resistant to fatigue. The new bolt cost just $3 per unit, negligible compared to the cost of a Merlin engine or a whole aircraft, but its importance was monumental. Rolling out the improved bolt was a massive logistical challenge. Millions of bolts were already in use, and the entire production line needed to halt or retrofit parts to prevent failures. Rolls-Royce collaborated closely with subcontractors, shipping plants, and maintenance depots to identify and replace suspect bolts as quickly as possible. Special inspection teams were dispatched across the UK and forward air bases. Meanwhile, training programs were implemented to ensure furnace operators understood the critical nature of the heat treatment process. New quality assurance protocols included hardness testing and batch tracking. Within months, the number of bolt failures plummeted. Merlin engines regained their reliability, and aircraft availability rebounded sharply. The ripple effect of solving the bolt crisis was profound. RAF fighter squadrons could fly more sorties with fewer mechanical losses. Bomber crews could rely on their aircraft to reach targets and return safely. The Merlin's reputation as a robust and powerful engine was restored. This improvement was timely. The Allies were ramping up bombing campaigns over Germany, and the Merlin-powered aircraft played crucial roles in reconnaissance, night fighting, and precision strikes. The morale boost among air crews and ground crews was palpable, knowing that the mechanical heart of their aircraft was no longer vulnerable to an obscure but deadly weakness. Renewed confidence. In the broader picture, the $3 bolt was emblematic of the critical importance of industrial quality and attention to detail during total war. It illustrated how even the smallest parts, when neglected, could jeopardize the most advanced technology and the fate of nations. The story of the Merlin bolt crisis is a powerful reminder that wars are not won by machines alone, but by the invisible networks of skilled workers, engineers, and supply chains. It reveals how engineering excellence depends on precision at every level, from the grand designs of engines to the humble bolts holding them together. As the RAF soared over enemy territory, it was the countless unseen efforts, like those to save 8,400 Merlin engines from failure that turned the tide. As winter deepened in early 1943, far from the roaring engines of Spitfires and Lancasters lighting up the skies over Europe, a different kind of battle raged inside the smoke-blackened factories of Britain. Here, in the labyrinthine workshops of Rolls-Royce and its sprawling network of suppliers, men and women fought an unseen enemy, the insidious decay of quality amid the pressures of total war. The three-cylinder bolt that had begun to fail was just a symptom of a much deeper industrial malaise, one rooted in human factors, wartime desperation, and the dizzying scale of mass production. To save the Merlin engine and, by extension, the RAF's future, engineers had to dive deep into the tangled web of manufacturing, labor, and supply chains. At the outbreak of World War II, Rolls-Royce was a relatively small, elite engineering company famed for producing luxury cars and advanced aero engines. The Merlin engine was already a masterpiece of precision engineering, but demand during the war turned Rolls-Royce into a colossal war factory. By 1943, the company was producing around 2,000 Merlin engines per month. Yet, this staggering output was not confined to a single plant. To meet the insatiable demand, production was dispersed across multiple factories, subcontractors, and assembly lines spread across Britain. This decentralized production was a double-edged sword. On one hand, it provided resilience against bombing raids that targeted factories. On the other, it introduced variability in quality, especially when the materials and skilled labor required were in short supply. One of the greatest challenges was the rapid expansion and transformation of the workforce. Skilled machinists, engineers, and craftsmen were in short supply. Many were conscripted into the armed forces or transferred to more critical war roles. To fill the gap, Rolls-Royce and its suppliers hired tens of thousands of new workers, including women who entered factory floors for the first time in history. Known as the war workers or munitionettes, these women took on roles traditionally held by men, operating lathes, grinding bolts, assembling engines, and managing quality control. While their dedication was unquestioned, many were new to the demanding precision required for aero engine components. Training programs were hastily implemented, but the learning curve was steep. This labor transition contributed to production inconsistencies. Compounding the issue, many experienced workers were replaced by forced labor from occupied countries or by workers of varying skill levels conscripted into factory work. Language barriers and morale issues also impacted the consistency of manufacturing processes. The bolt failure was eventually traced to a critical stage in manufacturing known as heat treatment. Heat treatment was the process of carefully heating steel bolts to specific temperatures and cooling them at controlled rates to achieve the necessary balance of hardness and toughness. Too soft, and the bolt would deform under pressure. Too hard, and it would become brittle, prone to cracking or shattering under the intense vibrations inside an engine. Heat treatment required experienced furnace operators, precise control of temperature, and consistent procedures. Yet, wartime shortages meant many plants had to operate with outdated or poorly calibrated equipment. Reports indicated that several subcontractors' heat treatment facilities were overworked, with furnaces running at irregular temperatures. Operators, some newly trained or under immense pressure to meet deadlines, were inconsistent in applying required procedures. A pattern emerged. Bolts from these plants exhibited micro-fractures, invisible to the naked eye but fatal under real engine conditions. Before the war, Rolls-Royce maintained some of the highest quality control standards in engineering. Every component passed through rigorous inspection with batch testing and detailed records. Wartime production strained this system. To meet demand, many subcontractors were given looser oversight. Quality inspectors were overburdened or redeployed to other critical programs. Moreover, the enormous volume of parts made it impossible to test every bolt destructively. Instead, quality assurance relied on statistical sampling, a practice vulnerable to variation, especially if defective parts were clustered within certain batches. The three bolt failures highlighted a tragic flaw. Tiny defects that might pass initial inspections could lead to catastrophic engine failure mid-flight. The consequences of these small defects were devastating in human and operational terms. When a bolt failed during flight, the supercharger assembly, critical for delivering high-pressure air to the engine, could loosen or shatter. The result was sudden engine loss, often forcing pilots to abort missions or, worse, crash. Engine failures reduced sortie rates and strained maintenance crews already working overtime. For the RAF, every grounded aircraft meant fewer planes in the air, fewer missions flown, and more pressure on remaining crews and equipment. At a time when Allied forces were intensifying bombing campaigns and preparing for the invasion of Europe, mechanical reliability was non-negotiable. Inside the factory walls, workers were painfully aware of the stakes, even if their tasks seemed small. Mary Thompson, a young woman working as a heat treatment operator in a Midlands steel plant, recalled years later, "We knew the bolts were important. The men flying those planes depended on what we did, but it was so fast and exhausting. Sometimes we'd run the furnaces all night, and with little experience, mistakes happened. When I heard about the failures, I was scared. It felt like we were letting everyone down." Such stories were echoed across the country. Workers toiled under long hours, blackout conditions, rationed food, and constant fear of air raids. Yet their efforts were heroic. Recognizing the issue, many volunteered for extra training, and factory managers tightened controls despite production pressures. The response from Rolls-Royce engineers and metallurgists was swift and methodical. Thomas Harding and his colleagues initiated a full-scale metallurgical investigation, collecting thousands of failed bolt samples and analyzing them for structural defects. New non-destructive testing methods were developed, including ultrasonic inspections to detect internal cracks invisible to traditional inspection. The engineering team redesigned the bolt slightly, introducing changes in geometry and recommending a new grade of steel less sensitive to heat treatment variations. Collaborating with suppliers, Rolls-Royce instituted standardized heat treatment protocols and sent experienced technicians to train furnace operators nationwide. To reinforce quality assurance, random batch testing was supplemented by more frequent destructive testing and tighter supplier audits. Replacing millions of defective bolts scattered across production lines, assembly plants, and maintenance depots posed an enormous logistical challenge. The Air Ministry coordinated with Rolls-Royce, RAF maintenance units, and transportation networks to organize a massive recall and replacement program. Every Merlin engine was inspected, and suspect bolts were removed and replaced with the improved version. Maintenance crews received detailed bulletins explaining the problem and instructing on inspection techniques. Factories ramped up production of the new bolts, prioritizing supply to frontline squadrons. Despite wartime shortages of raw materials, priority allocations ensured steel and heat treatment capacity were focused on critical components like the bolts. By late 1943, the results of these efforts began to show. Bolt failure incidents dropped sharply. Engine reliability improved markedly, allowing RAF squadrons to fly more missions with less downtime. The Merlin engine's reputation was restored, and its performance enabled increasingly daring missions. The bolstered reliability also allowed innovations in aircraft design and tactics. Pilots could push their planes harder, knowing their engines could withstand the stresses. RAF leaders credited this hidden engineering victory as a decisive factor in maintaining air superiority and supporting the strategic bombing campaign that would weaken the German war machine. The Bolt crisis revealed deeper truths about modern warfare and technology. It was not enough to design superior machines. Victory depended on the entire industrial ecosystem supporting them. Material supply chains, skilled labor, production processes, quality control, and logistical coordination all had to function flawlessly under extraordinary pressure. The $3 bolt was a symbol of this interconnectedness, a tiny part whose failure threatened to unravel the entire war effort. In this sense, the crisis anticipated modern concepts of system reliability and supply chain management that remain critical in both military and civilian industries. After the war, Rolls-Royce institutionalized Many of the lessons learned during the Bolt crisis, the company invested heavily in materials, science, workforce training, and quality assurance. The experience also shaped post-war aircraft engine development, emphasizing manufacturing consistency alongside design innovation. For the RAF and the Allied war effort, the Thread-Bolt episode became a case study in how attention to detail and relentless problem-solving could save lives and turn the tide of battle. The crisis was ultimately a story about people, from factory workers like Mary Thompson, who labored through exhausting shifts, to engineers like Thomas Harding, who refused to accept failure. It was human dedication and ingenuity that overcame the odds. Their work went largely unseen by the public, overshadowed by dramatic aerial battles and political events. Yet without it, those victories would have been impossible. The bolt that saved the Merlin was more than metal. It was a testament to the power of perseverance, expertise, and the unbreakable spirit of those who built the engines of victory. The winter of 1943 had tested Britain's industrial might and resilience in ways few had anticipated. The $3 bolt, seemingly insignificant, had threatened to undermine the very heart of the Royal Air Force's strength, the Merlin engine. But through determination, innovation, and unyielding commitment, the crisis was overcome. The impact was not only technical, but strategic, shaping the course of the war and leaving a legacy that echoed long after the guns fell silent. As 1944 dawned, the atmosphere in Rolls-Royce and across the RAF was charged with a new sense of purpose. The lessons learned from the bolt failures had galvanized the entire production and maintenance system. The improved bolts, heat treatment protocols, and quality assurance measures were now fully integrated into the manufacturing cycle. This seamless coordination was no small feat. It required constant communication between engineers, factory managers, maintenance crews, and military leadership. This collaboration showcased the best of Britain's wartime ingenuity. It reflected a transition from reactive firefighting to proactive systems engineering, an approach that would influence post-war industry worldwide. Technological advancements accelerated to meet the challenges exposed by the Bolt crisis. Rolls-Royce engineers pioneered new testing equipment that allowed for rapid, non-destructive evaluation of components. Ultrasound and X-ray techniques were adapted from other fields to detect internal flaws without damaging parts. This dramatically improved the speed and reliability of inspections, ensuring defective parts could be identified before installation. The company also advanced metallurgical science, developing alloys more resistant to stress and fatigue. Research into heat treatment became more sophisticated, involving detailed mapping of furnace temperatures and advanced controls. The wartime urgency compressed years of innovation into months, a testament to how necessity drives rapid technological progress. While the technical story of the $3 bolt is compelling, it must not obscure the human cost behind it. Pilots like squadron leader James "Jimmy" Hawks knew firsthand the deadly stakes of engine failure. In a letter to his wife from 1943, Hawks wrote, "Every time I climb into the cockpit, I trust not just my skills, but the work of thousands of men I'll never meet. A tiny bolt can mean the difference between life and death. Knowing the factories are fixing these problems keeps me flying." Many service personnel lost their lives or were wounded due to mechanical failures, and the pressure to solve these issues weighed heavily on engineers and workers alike. Across Britain, factory workers endured exhausting shifts, ration shortages, and constant air raid threats, all while striving to perfect machines that would help end the war. The restored reliability of the Merlin engine had a direct and profound effect on the Allied war effort. In 1944, the Allies launched Operation Overlord, the massive invasion of Normandy that marked the beginning of the end for Nazi Germany. Air superiority was crucial to the success of the invasion, and Merlin-powered aircraft were at the forefront. Spitfires and Mustangs provided close air support, hunted enemy fighters, and protected bomber formations. The improved reliability meant fewer aborted missions and mechanical losses, allowing the RAF to maintain relentless pressure on German defenses. Moreover, the Merlin engine powered the legendary Avro Lancaster bombers, which carried out devastating nighttime raids that crippled German industry and infrastructure. The 300 Bolt story was thus inseparable from the broader Allied victory, a reminder that tiny components could sway the fate of nations. After the guns fell silent in 1945, the industrial and military communities reflected on the lessons learned from the war. The 300 Bolt episode became a case study in quality management and supply chain reliability. Engineers recognized that design excellence alone was insufficient. Consistent manufacturing quality was equally vital. This understanding seeded the development of formal quality control systems, such as statistical process control, SPC, and total quality management, TQM, which would transform manufacturing worldwide in the decades to come. Rolls-Royce became a pioneer in adopting these principles, applying rigorous standards not only in aero engines but across all its products. Despite its significance, the Bolt crisis and its resolution remained largely unknown outside engineering circles. Historians and aviation enthusiasts have since uncovered the story through archives and personal accounts, shining light on the countless unsung heroes, the factory workers, metallurgists, furnace operators, and engineers, whose relentless work saved the Merlin engine. Mary Thompson's wartime memoirs were published decades later, offering a poignant glimpse into the lives behind the machines. She wrote, "We never imagined our small tasks could make such a difference, but when you held that finished bolt in your hand, you knew a pilot's life depended on it. It was a heavy responsibility, but we carried it with pride." The 300 Bolt stands as a symbol of how small details matter in great endeavors. It epitomizes the interconnectedness of technology, human skill, and management in modern warfare. In a broader sense, it teaches a universal lesson. Even the mightiest machines and grandest plans rely on the integrity of tiny parts, from the cockpit of a Spitfire soaring above the clouds to the furnace operator adjusting temperatures deep underground. Victory was forged through shared dedication and precision. Today, as industries grapple with complex global supply chains and ever higher technological standards, the story of the Merlin Bolt resonates anew. Manufacturers, engineers, and managers study this history as a cautionary tale and inspiration. It highlights the need for rigorous quality assurance across all suppliers, skilled workforce development and continuous training, clear communication and rapid problem-solving mechanisms, investment in advanced testing and inspection technologies. These principles remain as relevant in aerospace, automotive, electronics, and many other fields as they were in 1943. The saga of the $3 Bolt is a testament to the power of focus, collaboration, and determination in the face of adversity. By saving the Merlin engine, a tiny piece of metal helped ensure that Britain's skies remained filled with the roar of Spitfires and Lancasters, a roar that heralded freedom and hope. It reminds us that behind every great victory lie countless small acts of courage, ingenuity, and care. The Merlin engine's roar was more than machinery. It was the heartbeat of a nation's resolve, and at its heart, the humble $3 Bolt held firm. The war had ended, but the story of the $3 Bolt and the Merlin engine was far from over. As Europe struggled to rebuild and the world shifted into a new era, the lessons learned from wartime engineering crises shaped the future of aviation, industry, and quality assurance. This chapter explores the Bolt's enduring legacy, the evolution of Rolls-Royce in the post-war years, and how the meticulous attention to small parts continues to define modern engineering excellence. May 1945 marked the formal end of the conflict in Europe. The Allies had triumphed, and the Merlin engine had proven itself a crucial element of that victory. Yet peace brought new challenges for Rolls-Royce and the broader aviation industry. Wartime production had focused on volume, speed, and durability under combat conditions. Now, a transition to peacetime demanded innovation, refinement, and new designs. The Merlin's successor engines, like the Rolls-Royce Griffon and later the legendary Rolls-Royce Avon jet engine, benefited from the wartime lessons about materials, manufacturing, and quality control. The Bolt crisis had exposed vulnerabilities, but also prompted systemic changes that positioned Rolls-Royce to lead in post-war aero engine development. The company applied rigorous standards, learned from the Merlin program across all new designs. The intense scrutiny of every Merlin engine bolt had forced Rolls-Royce and its suppliers to pioneer quality control methods that were revolutionary at the time. Prior to the war, quality assurance in manufacturing was often inconsistent and localized. The bolt failures forced the introduction of standardized testing procedures, inspection regimes, and documentation protocols. Statistical methods began to be widely adopted. Engineers used sampling techniques and data analysis to predict failure rates and optimize processes. This was a dramatic shift from reactive inspection to proactive prevention. These practices formed the foundation of what would later be called total quality management and Six Sigma. Rolls-Royce became an exemplar of industrial quality, with many of its post-war successes tied to these principles, while technology and management systems were essential. The war also underscored the critical importance of the human element in manufacturing. The factory workers, many of whom were women entering industrial labor for the first time, underwent rigorous training to meet exacting standards. The three-dollar bolt crisis taught that even minor lapses could cause catastrophic failures. Post-war, Rolls-Royce invested heavily in workforce development. Apprenticeships, specialized training programs, and cross-disciplinary cooperation became standard practice. Morale and pride in craftsmanship remained a cornerstone of the company culture, a legacy rooted deeply in the wartime experience. The wartime bottleneck around a simple bolt revealed the dangers of over-reliance on single sources for critical components. After the war, Rolls-Royce diversified its supplier base and developed more robust supply chain management strategies. It cultivated relationships with multiple vendors worldwide, balancing cost, quality, and risk. These efforts foreshadowed the complex global supply chains of the modern era, demonstrating early awareness of vulnerabilities that would later challenge many industries. The Merlin engine, with its characteristic rumble, became a symbol of piston engine supremacy. But the post-war years ushered in the jet age, radically transforming aviation. Rolls-Royce led the way with the development of the Avon and later the Conway, the world's first turbofan engine, cementing its position as a premier aero engine manufacturer. The attention to detail that saved the Merlin bolt carried over into jet engine design and production. The company's culture of precision engineering, founded in part on lessons from the bolt crisis, enabled Rolls-Royce to innovate rapidly while maintaining reliability. Beyond its literal function, the $300 bolt came to symbolize a broader set of principles relevant to engineering, management, and leadership. It illustrated that no part, task, or person is too small to matter. Success in complex systems depends on the integrity of every component and process. This metaphor was embraced in post-war industrial management theories, emphasizing systems thinking, accountability, and continuous improvement. Leaders across sectors cited the Bolt story to demonstrate how attention to detail and teamwork could avert disasters and create competitive advantage. Though initially an obscure technical matter, the $300 Bolt story eventually permeated popular culture and history. Documentaries, museum exhibits, and aviation history books highlighted how tiny, inexpensive parts could influence the outcome of great events. Rolls-Royce itself honored the legacy by preserving original Merlin engines and components in museums, educating future generations on the importance of quality and perseverance. Preparing and narrating this story took us a lot of time, so if you're enjoying it, like this video, it means a lot to us. Now back to the story. Veterans and engineers shared oral histories that kept alive the memory of the crisis and the collective effort to overcome it. The quest to perfect the $300 bolt inspired ongoing research into new materials, coatings, and manufacturing methods. Advances in metallurgy introduced alloys with superior strength, fatigue, resistance, and corrosion protection. Manufacturing embraced automation, computer-controlled machining, and additive manufacturing, 3D printing, dramatically enhancing precision. These innovations have roots in wartime imperatives to produce reliable, high-performance components at scale. Modern commercial and military aircraft owe a profound debt to the Merlin engine and the wartime crisis that tested its components. The emphasis on reliability, maintainability, and modular design in today's engines can trace lineage back to practices refined during the Merlin's production. Rolls-Royce remains a global leader in aero engines, driven by a commitment to quality born from historical experience. The $300 bolt crisis also serves as a reminder of how risk and resilience coexist in engineering. Risk is inevitable, especially in complex, high-performance systems. What matters is the capacity to identify, manage, and mitigate that risk quickly. The story demonstrates the importance of feedback loops, listening to frontline workers, integrating test data, and adapting processes. This resilience mindset has become a cornerstone in fields as varied as aerospace, automotive, software, and infrastructure engineering. In an era defined by rapid technological change, global challenges, and complex supply chains, the lessons from the ceaseless bolt remain remarkably relevant. Industries today face similar risks, from microchip shortages to cybersecurity threats, where small vulnerabilities can have outsized impacts. The story encourages companies and governments to invest in quality systems, workforce training, and diversified sourcing. It also highlights the value of historical awareness. Understanding past challenges can illuminate paths through present difficulties. The humble $3 bolt, once an anonymous piece of hardware, became a linchpin in one of history's most critical engineering challenges. Its story underscores how grand achievements often hinge on small, precise, and well-crafted components. From the skies over wartime Europe to the boardrooms of modern industry, the bolt symbolizes the fusion of human skill, scientific innovation, and managerial foresight. As we look to future frontiers, whether in aerospace, energy, or technology, remembering the bolt's journey reminds us that greatness is forged in the details. The story of the $3 bolt and the Merlin engine is often told through the lens of engineering and technology. But behind every technical breakthrough lies a tapestry of human effort. Scientists, engineers, factory workers, pilots, and managers, whose dedication and determination made victory possible. This chapter honors those unsung heroes, exploring the human side of the Merlin engine's saga and how teamwork and tenacity forged success from adversity. At the heart of the Merlin engine's success were the engineers who designed, tested, and refined it, people like Sir Stanley Hooker, whose expertise in supercharging turbo systems helped unlock the engine's extraordinary power, and Ernest Hives, Rolls-Royce's managing director, who steered the company through difficult times with vision and decisiveness. When the 3D bolt crisis erupted, it was the engineers who first identified the problem and understood its implications. Their analytical minds combed through the failure reports, reviewed materials data, and re-examined manufacturing processes. These men and women knew that the engine's reliability depended on more than just design. It hinged on flawless execution, down to the smallest part. Yet, their work wasn't confined to technical problem-solving. They became communicators, liaisons and leaders, working closely with factory supervisors and suppliers to implement changes. They navigated industrial politics and wartime pressures, balancing urgency with precision. Their ability to adapt and innovate under fire was crucial. While engineers provided designs and solutions, it was the factory workers who brought the Merlin engine and its critical components to life. Many of these workers were women recruited under the wartime factory girl programs, stepping into skilled roles traditionally held by men. These workers learned new skills rapidly, mastering complex machining, assembly, and quality inspection techniques. Their hands and eyes ensured that every bolt, piston, and valve met stringent standards. They worked long shifts in difficult conditions, often under the threat of air raids and shortages, the three-to-bolt crisis placed extraordinary demands on these workers, changing materials, refining tolerances, and implementing new testing procedures required meticulous attention and adaptability. Errors were costly, not just in dollars, but in lives and war outcomes. Factory workers showed resilience and pride. Many understood that their work was directly connected to pilots' lives and the broader war effort. Their contributions were vital, even if largely unrecognized at the time. At the other end of the Merlin's journey were the pilots who flew Spitfires, Hurricanes, Lancasters, and Mustangs, powered by this engine. For them, the engine was not just a mechanical marvel, it was a lifeline. When a pilot throttled the Merlin's twin supercharged cylinders, he trusted that every component had been built and tested to perfection. The $3 bolt failure had shaken that trust during the crisis, but the swift response from engineers and manufacturers restored it. Pilots reported the Merlin's reliability and performance with admiration. Many credited the engine with giving them a fighting chance in dogfights, long-range reconnaissance, and precision bombing missions. The bond between the pilots and those who built their machines, though often unseen, was deeply felt. Letters and memoirs from airmen frequently expressed gratitude toward the men and women on the production lines whose work kept them airborne. Behind the scenes, managers and leaders coordinated the vast effort required to produce tens of thousands of Merlin engines during wartime. Figures like Ernest Hives exemplified leadership that combined technical knowledge, industrial savvy, and human empathy. Hives championed the adoption of rigorous quality controls after the Bolt crisis and fostered a culture of continuous improvement. Government officials and military leaders also played crucial roles. They facilitated resource allocation, prioritized production schedules, and supported innovation through funding and policy. Managing Rolls-Royce's extensive supplier network, workforce, and engineering teams under wartime constraints was a monumental challenge. The ability to orchestrate this complex system proved decisive. The Merlin engine's story is also one of collaboration. Rolls-Royce worked closely with the British government's Ministry of Aircraft Production, the Royal Air Force, and numerous suppliers across the country. Material scientists developed new alloys and adhesives, metallurgists tested fatigue resistance, and chemists improved lubricants. Test pilots flew prototype engines under rigorous conditions to validate designs. This cross-disciplinary cooperation exemplified the best of wartime innovation, breaking down silos to focus on shared goals. Information flowed rapidly, and feedback loops accelerated improvements. Such collaboration was essential in overcoming the $3 bolt crisis and maintaining Merlin production at unprecedented scales. While the $3 bolt may seem like a small technical detail, its failure had real human consequences. Engine breakdowns could result in aircraft loss and death. Many workers labored under stressful conditions, including air raids that damaged factories and threatened lives. The pressure to produce engines quickly without compromising quality was immense. Pilots faced mortal danger every time they took off, trusting in the integrity of the machinery. The awareness of the stakes infused every aspect of the Merlin's production. The crisis and the war exacted a toll on mental and physical health, yet the workforce persevered, driven by a shared sense of purpose. Among the countless individuals involved, certain stories stand out. One machinist, Margaret Collins, recalled working overtime to hand-inspect bolts when quality control procedures ramped up after failures were discovered. She described the tension, but also the pride in knowing her work kept planes flying. Another engineer, James Holloway, spent sleepless nights analyzing metallurgical reports, searching for causes of unexpected corrosion in certain bolt batches. His determination eventually led to adopting better materials. Test pilot Eric Saunders credited the Merlin's reliability to the factory workers' attention to detail, famously saying, "Every time I took off, I felt a quiet thank you to those I'd never met, who made sure the engine held together." These personal accounts reveal the human dimension behind the Bolt story. For decades after the war, Much of this labor remained anonymous. The focus was often on frontline heroes rather than factory workers or engineers. But gradually, recognition grew. Rolls-Royce and various historical organizations began to honor the contributions of their wartime workforce. Museums featured exhibits on the Merlin engine and its makers, telling the stories of those who toiled in factories and offices. In 2015, Rolls-Royce inaugurated an annual Quality Day, dedicated to remembering the lessons of the $3 bolt and celebrating excellence in manufacturing. Such recognition helped restore balance to the narrative, acknowledging that victory depended on a vast network of people united by a shared mission. The $3 bolt crisis illustrated that success depended not only on brilliant ideas, but on leadership that valued communication, collaboration, and humility. Leaders who listened to engineers and factory workers, who understood the realities of production, and who fostered a culture of accountability were best positioned to overcome challenges. This human-centered approach is as relevant today as it was during World War II, reminding modern organizations that people, not just machines or plans, are the ultimate resource. The $3 bolt story is a testament to the power of human determination, skill, and cooperation. From the engineers who solved the problem, to the workers who produced every part with care, to the pilots who trusted their machines, the Merlin engine was a collective achievement. Their combined efforts helped turn the tide of war and left a legacy of innovation and quality that endures. In honoring these unsung heroes, we remember that history is made not just by great events, but by the countless small acts of dedication and excellence. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.